All right. Let's watch this guy, Derivation of Brachistochrone, Euler-Lagrange equation. Feels good. So I started watching it. Looks interesting. So far, I haven't seen basically anyone who uses any usage of this equation. So let's see it.
Is constant. And that means that mv squared over 2 plus mg. And then notice that mg is weaker.
Okay, but this has nothing to do with the Euler-Lagrange. Euler-Lagrange, the Lagrange uses t minus v. The Hamiltonian is t plus v. So I don't know why he's doing this. So over here he did, let me see that you can see it, yeah. Let me give you the link so you can join. So, so what did he do? So he said this method minimizes the time. This is the first time I'm hearing this. That the claim is that whatever path is chosen, nature chooses the path that takes the least time. That's the least action. It's actually the least time. No one has said this. And why do you claim this? What is the foundation of this? So we saw a video yesterday, the derivation of the Euler-Lagrange equation, that minimizing, if we minimize this, then that's nature. I don't remember exactly how they did it. Okay. So S is the action, and the integral S is the path. Each one of these paths is an S. Each one we integrate over time, and we choose the one that is the least. The least S is the answer, is nature's choice. Now dt, it's very interesting. So dt is just converting dt. He's just saying dt is equal to dt times 1, and ds over ds is 1. So dt over ds is ds over dt2 minus 1, which is ds over t. ds over dt is v. And ds is the square root of dx squared plus dy squared. So far, so good. And then he says that E equals T plus V, and it's a constant. There's no friction, there's no energy loss. Now E is T plus V. T is mv squared over 2, 1 half mv squared, and V is mg. Right, and the question is, if we drop a ball over here and we let it choose any path it wants, what is the fastest path? Oh, the question is, what is the fastest path? This has nothing to do with the least action. The question is, which path is the fastest? So it's a different question than the least action. This has nothing to do with the least action. So the question is, what is the fastest path? What is the least action? That's an interesting question. What is the least action or their least time? Which path is the fastest? Okay, that's a different question than the least action.
The smaller y gets. So I'm going to write it as this.
So what did he say?
And then notice that mg is weaker the smaller y gets. So I'm going to write it as this. mg minus y.
So it's mg minus y. Y is y in this direction? Which is y? Is up y or is down y? I'm not sure what he means. Is this positive y or is this negative y? I don't know. I mean, this is positive x, and this is the arrow of positive y. So he says, so the lower it gets, the weaker it gets, the weaker the energy. So what did he say?
mg is weaker the smaller y gets.
So this is mgy, and this is also mgy, but over here there's less potential energy. So this is a smaller y. I don't understand what he means. I don't understand. I don't understand what he means. I don't know what he means. MGY, right? The higher the Y is, the higher MG is. What's going on here? I don't understand.
mg minus y.
Oh, he's going to change his mind.
Is that even good?
No, it's not.
It is good.
No, it's not.
Yes, as minus y.
No, it's not.
No, it isn't.
It's
good. I would need to draw it like this. Yes. That's the thing. So I want y to be increasing like this.
Oh, okay.
In this case, it's minus y.
Yes, in that case,
yes. If in negative y over here, we would have positive potential energy. This is where our potential energy is 0. So this is V equals 0. Yep. And this is why we get minus y. So this would be constant. Now,
so the bigger y is, as y grows, energy, the potential energy is lower. So, yeah. So the smaller, so as y tends to negative, you have more potential. So the potential becomes positive. Okay. Makes sense.
Constant, then we can just plug in y equals 0 and get the value for mv squared over 2. So what I mean is get the value for the constant. So we know that the velocity of 0 is 0. This is one of our initial conditions. V of time is 0.
Okay, so the assumption is time equals 0, it's not moving. Okay, let me just subscribe. Okay. So V at 0 equals 0.
Time equals 0 is 0. And let me just note that x of time equals 0 is 0.
Right.
And y of time equals 0 is 0. So both x and y are increasing with respect to time.
We also know that at t equals final, t equals 1, t1, x and y is x naught, y naught, but we don't know the velocities.
So if the velocity at t equals 0 is 0, and y of 0 equals 0, then that means that the constant is equal to 0, right? Because we have 0.
Well, the assumption is, okay, I mean, you're just assuming there it starts from 0. So yeah, there's no, that's impossible. The total energy is mgh. It should be mg y naught. What do you mean 0? mv squared, let's plug in t equals 0. V, okay, this is 0. So the kinetic energy is 0. But y, oh, he's saying that y at 0 equals 0. Okay, so the total energy is defined as 0. It doesn't matter, some constant.
0 plus 0 equals constant. And this means, in turn, that mv squared over 2 is equal to mgy. So we have that v
Yes.
is just a v of y. Okay?
Okay, so v, so m drops out. So I guess you multiply by 2. So v squared is equal to 2y, or v is equal to the square root, 2g of 2gy. What do you mean v equals v at y? V is a function of y. Well, it's a function of time, but y is a function of time, so I guess you could say that. What did he say?
Squared over 2 is equal to mgy. So we have that v is just a v of y. Okay?
Oh, when you look at this, it's not a function of m, and g is a constant, so v is a function of y. Okay.
Velocity completely can be expressed just through the y variable. So here, let's just express it then. So
it's 2gy. It's the square root of 2gy. The positive and negative square root of 2gy. But why is it positive and negative square root of 2gy?
v is the square root of 2gy. All right. And then we're going to want to use this. So we're going to be putting our v in there. And we have the action equal to the integral of,
Yeah, you should show, as you're plugging it in, you should definitely show it. So it's ds times v, or ds over v. ds dt, it's 1 over ds dt, so it's 1 over v. So it's ds over v. So it's the integral of ds over v.
we have ds over v. Now ds is dx squared plus dy squared. I'm leaving it in this format intentionally for now.
It's not a format, it's a form. Okay, so this is ds, and now v, and v is the square root of 2gy.
2gy. Now you'll notice that I can take 1 over square root 2g in front. It's just a constant. We don't care about.
Right. 1 over square root of 2g is a constant. Right.
It when we're minimizing, so I'm not going to keep writing it. Here we have the square root of y, and now we need the differential to integrate over. Now, it is going to be much simpler to treat this as x of y instead.
This is interesting. I've never seen this form that you have dx squared plus dy squared. So what are we integrating? What is the integral, not the integrand, but what is the integral variable? What are the infinitesimal differential? What are the differentials that we're integrating?
As y.
I guess they are dx and dy somehow. I've never seen this form.
Of x to differential to integrate over. Now, it is going to be much simpler to treat this as x of y instead of as y of x. You can try both ways, and it's not much different, but it is going to be simpler for our calculations. So what I'm going to do is I'm going to take out dy, and I'm going to treat y as the independent variable. So in the square root, I'm going to have...
So he needs to take out dy. So he took out dy. Now let's see what he ends up with inside. So if you take dy, you have to take dy. I don't know. I mean, let's see what he does.
X prime squared plus 1, where x prime is defined to be dx over dy. There we
Oh my god, why do they skip so many steps? So x prime squared is the x dy squared, which is the x squared over dy squared plus dy squared over dy, I guess. Jesus Christ. Show the steps. I mean, you're making a video. Show the steps.
There we go. And now, if we recall the Euler-Lagrange equations, for the variation to be 0, the variation of the action, we need to have, and this is our Lagrangian, the whole thing, in between the integral and dy.
Why do you have to say that? All you have to do is just say that the differential, right? This is a function. This is a functional. It's a function of a function or something. So you want to perturb this system and show that any perturbation, yeah, I don't know.
We need to have that d by d, the independent variable. So this is where we put y, partial Lagrangian by partial x prime minus partial Lagrangian partial x equals 0. So this is what needs to hold.
Mm-hmm. Mm-hmm. Okay, this is the Euler-Lagrange equation. The differential. Let me just check. No one is watching. That's good. La 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 la. So what is he saying? Okay, so he's saying this is our Lagrange, whatever that is. I would just say that you want this, right? This is the action. This is the action, and you want its derivative, but with respect to what? Its derivative with respect to what? Right? You want any eta with respect to epsilon. There's no epsilon here. So we already went through the calculation with the epsilon. And this was our conclusion, that when delta S equals 0, because what are we saying? We're saying that there's many possible S's. We don't know which S. We don't know which S, but we don't know which Y, which function Y is the best one, is the optimal. We don't know. But for any function y, we know for a bunch of functions, for all the functions that we could ever come up with, we know we would get different s's, which are just different times. S should be in the form of time. So we should be getting different times. There's different functions we can select. We could do this computationally, like using a computer, we can write a computer program and let it try out different paths and see which one gives us the smallest s. So try this path and this path and this path and this path, and then it's going to optimize a certain path such that any modification we make to this path will increase s. Any modification we try and make to this path will increment it. And then we would say, oh, we found it. So that's a computational approach. It has another name. Analytic, I think they call this. Numerical, maybe. Let me take a sip of water. Okay. So Euler-Lagrange says that this must be true for that path. That any modification, let's start from here, any modification with to the Lagrange to this with respect to x, so this Lagrange or Lagrangian any modification we make to the Lagrangian, no, any modification, right? So there's different paths. For each path, this is the time that it will take. For each path, this is the time that it will take. For that path, for that Lagrangian, Lagrange function, for any path, we're going to compare paths. For any path, this would be, okay, this function, okay, so there's x and y, but y is y a function of x? Yes. Y is some function of x. Notice that there's no time. There's no t. So we can imagine there's just an x and a y and an L. So we can imagine a three-dimensional terrain where we have the x and the y make up a plane, and the Lagrangian is the mountain. But x prime, oh, we're saying that x is a function of y. Okay. It doesn't matter. So y is the independent variable, and we're going to have an x prime. So for we need to draw this. La 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 la. Okay, so the way I would draw it is usually this is the y, and this is the x, and this is the Lagrangian. The Lagrangian is a function of x and y. However, because I always like looking at things geometrically, I find everything to make much more sense when we draw the geometry. What are we saying here? We're saying that we have an independent variable y and a dependent variable x. So x is the function. But notice, right, what are we saying? We're saying that, remember the question. The question was, we started at x equals 0, y equals 0. This was the starting point. And we let it go to y negative and some x. So this was the final point of the trajectory. So the trajectory would end up being something like this. That's the brachio. That's the brachistochrone. Brachistochrone. Okay. That's the shape. That's the shape of the fastest path. Okay. So the question is what? For each path, there's a Lagrangian? It's not, so it's not a terrain. Or it is a terrain, it's just that it doesn't matter what the x is. And it doesn't matter what y is. It's a function. So for each path that is described actually by x, by the way, I don't understand. If y is the independent variable, notice that you have a violation of uniqueness. For this y, there's two x's. So that's like so x cannot be defined as a function of y. So when he says that x prime is dx dy, this assumes that x is a function of y, but that does not hold. X cannot be a function of y in this problem, the way he posed it. So when was this done? This is 3 years ago. Really strange. I don't know what to say about that. He's saying that it's by definition. Oh yeah, that's just the definition. X prime is just dx dy. We're at 7:40. When did he say this? He said it basically over here.
But it is going to be simpler for our calculations. So what I'm going to do is I'm going to take out much of it. We have the square root of y, and now we need the differential to integrate over. Now, it is going to be much simpler to treat this as x of y instead of as y of x. You can try both ways, and it's not much different, but it is going to be simpler for our calculation.
How can you say it's x of y? Look at your geometry. This is x and this is y. And here you have, for a specific y, you have two x's. So how can you treat this as x of y? I don't know. No, we didn't get here yet.
To do is I'm going to take out dy, and I'm going to treat y as the independent variable. So
you can't. 6:38. I'm going to treat y as the independent variable. You can't. For the way you drew the path of the solution, there are two x values or two y values. Oops. There's x and another x. There's two x values. There are two x values. This is a violation of the definition of a function. X cannot be a function of y. Y cannot be treated as the independent variable. I don't know. I don't know.
So what we get minus partial Lagrangian partial x equals 0. So this is what needs to hold. Well,
okay. So I'm assuming x is a function of y. So for the solution of the function x, any modification so as we modify for the solution, where this holds, where delta S is 0, for that solution, for the optimal solution, any modification to X will bring about a modification to the Lagrangian. And any modification right, so the Lagrangian is a function of X and X prime, not of X and Y. But it says here the Lagrangian is a function of X prime and Y. So it's also a function of Y. I don't know. I'm trying to visualize this equation. This is, I don't know. Okay, so, and this says that, okay, this is the modification. The modification that we get to the Lagrangian from this, if we modify the function x, which does not show up here, but x prime shows up. Okay, so if we modify any modification to the function, to the path, x is the path according to him. So any modification to the path causes a modification to the Lagrangian, okay? And any modification to the path, to the derivative of the path, again causes modification to the Lagrangian. And if we take this ratio and we take the derivative with reference to y, so the Lagrangian is not well, this partial derivative is only with respect to x prime, not to y. So whatever y ends up here. Okay, the next thing is to actually do this derivation, to do this derivative.
We need to differentiate everything. But luckily, this part here is just equal to 0. So what we get is that d by dy.
What do you mean it's 0? It doesn't show up, okay.
Of the partial of the Lagrangian with respect to x prime is equal to 0. That just means that this quantity is a constant. So let's call it c. Let's call it c, and let's differentiate it.
So he says, okay, so the left term is equal to 0 then. The derivative of this is equal to 0, which means this is a constant. If the derivative is 0, then this is a constant, okay?
The square root is going to be going down. X prime
so now
plus 1.
He's actually taking the Lagrangian and he's doing a derivative with respect to x prime. So it's, let's see what he does.
And square root y, 1 over. And of course we would have a 2, which is going to get lost. So x prime. This is equal to c.
So this is the derivative. I'm assuming this is the derivative. So this is with respect to only x prime. So he's assuming y is a constant, maybe. So if y is a constant, it comes out, and all you're doing is just bringing this goes down by 1 power, and the internal, the okay, whatever, it's the derivative of this thing. I'm not going to do this now, okay?
And now we square both sides, and multiply with the square roots. So we have x prime squared is c y x prime squared plus 1. Okay.
Yeah.
We can express with respect to x prime.
It's
Square,
just
let's keep squared. 1 minus cy equals cy. And x prime
I don't get it. What did he just do? 1 minus cy. What? Oh my god. Why do they skip steps? X prime squared. If cy is here, then he must be dividing by this thing, but he's not dividing by that. What is 1 minus cy? What is that? Where's that from? X prime squared makes sense. Cy squared makes sense. So he just took x prime squared plus 1 and he should have divided by it. But instead he's multiplying by 1 minus cy. Why?
prime is the square root of cy, 1 minus cy. There we go.
X prime is cy1 minus cy square root. But how did he do all that? What am I missing? Why is there a 1 minus cy on the left here? Where's this from?
Now this is integrable. A lot of people like to express this with respect to an independent parameter, phi. So we parameterize x and y with respect to phi. If I were to do this immediately, it would be sort of like an ansatz, like I'm suggesting the solution. Now I could do that, but I seem to prefer actually solving it first, since it is a solvable one.
I don't get it. What just happened? This is simple algebra. What am I missing? Let's bring this here, so it's x prime squared. Oh my god. Oh. So this is, if we bring x prime squared plus 1 over here, how did he get, what is this? X prime squared times 1, okay, so what if we actually, this is cy x prime squared plus cy. So cy is here. So, okay. So this is cy times x prime squared. So this is x prime squared minus cy x prime. So x prime squared is factored out. So it's 1 plus cy. Or 1 minus cy times x prime squared. Okay. Now I got it. Fine. Everything is fine. So now he's saying x prime is equal to the square root of cy over 1 minus cy. Okay, so what's the next step? So phi?
We just have the dx is the square root of cy, 1 minus cy dy.
So this is dx dy. We defined it as dx dy. So dx dy Or this is dx times this dy, okay.
And we can solve for x here. It does take a little bit of a long time, and I'm worried that I'm gonna make a mistake. Let's see how it turns out. Okay, so integrate both sides, and I'll just be looking at this. Let's call that I. So I is the square root of cy over 1 minus cy dy. First of all, I'll multiply by c and divide by c. So I could have cy is equal to
Phi.
When I have sine squared theta, let's say, so that this part becomes cosine, okay?
So cy is going to be sine squared theta. So 1 minus cy is 1 minus cosine. Sorry, is cosine squared theta.
So cy is sine squared theta. That means that
One.
the cy is 2 sine theta cosine theta d theta.
Okay.
Which is sine 2 theta, by the way. So the integral is 1 over c. Integral. Let's put dcy first. So that's 2 sine theta cos theta.
Okay, so the 2 goes, okay, and then he's copying the dcy, I guess, and he's going to put the d theta at the end.
Theta.
Sine theta cosine
D theta.
theta. Okay, d theta.
And then we have cy is sine squared.
This is dcy. This is just this. Next is, this looks like sine theta over cosine theta.
Theta, so that's sine theta. And 1 minus cy is 1 minus sine squared, which is cosine squared. The square root is cosine theta. So this part and this part dies, and we have 2 sine squared theta.
Right.
Now note that 2 sine squared theta is, well, 1 minus this is cosine 2 theta. So that means,
let's see. So we have 2 sine squared theta d theta. Okay, so 2 sine squared. So what is he saying? He's saying 2 sine squared. So he's putting a 1 minus here. And he's saying this would equal to cosine 2 theta. Well, I don't know why you would say that.
2 sine squared theta is 1 minus cosine 2 theta. That is, well, 1 minus this is cosine 2 theta. So that means that 2 sine squared theta is 1.
But why 1 minus 2 sine squared theta is equal to cosine 2 theta? Okay, that's, I guess that's like some identity. That's some identity because 1 is equal to sine squared plus cosine squared. I don't know how you, I don't know. And maybe he's using derivative. I don't know how you get this identity.
Minus cosine 2 theta. So we have 1 over c, the integral of 1 minus cosine 2 theta d theta.
So this is 1. So we had 2 sine squared theta d theta. So d theta is fine. 2 sine squared. Oh, because okay. So this is 1 minus 2 theta. Okay.
And that's equal to theta over c. Oh, okay. 1 over c. Theta minus 1 over 2 sine 2 theta.
This is why people make mistakes, because They skip so many steps. They want to do everything in their mind.
We can write sine 2 theta as 2 sine theta cosine theta, like this. Okay, there we go. That's it. That's the whole thing. So 1 over c theta minus sine.
Is he in America with that noisy floor? It sounds like he's in Europe by his accent.
Sine theta cosine theta.
Only in America you have these noisy floors, unless, I don't know, maybe in Europe too.
And plus some other constant, huh? Guess we don't need it, do we?
Wait, what was the question?
So 1 over c theta minus sine theta cosine theta.
Oh, because of the integral, he needs to add another constant. Should be plus d.
Plus some other constant, huh? Guess we don't need it, do we?
You can add it, and then this would be the initial, per the initial conditions, it could drop out if it's 0.
I guess I could always assume that it doesn't exist. Let's include it for now, and I'll see. In any case, so we have that sine theta. Sine theta is square root cy, and cosine.
Sine theta. Okay, so cy was sine squared theta, right? So we solved it for theta, but now we need to solve it for x and y. So how do you convert theta to x and y? So this is the ratio of, or this is, yeah, the relationship between y and theta. So we need to convert sine theta. We need to convert theta, sine theta, and cosine theta. So theta, I guess it's, I don't know what it is, but so sine theta is the square root of cy. Now you can take the derivative of both sides. I don't know if that's going to help you. With respect to what?
Theta is then just 1 minus sine squared theta. So this integral with respect to y, with respect to cy, is 1 over c. So theta is the inverse sine inverse of square root cy. And then
that's theta. So we need to convert theta into x and y. So what's the conversion? Theta is sine inverse of the square root of cy.
And cosine theta is then just 1 minus sine squared theta. So this integral with respect to y, with respect to cy, is 1 over c. So theta is the inverse sine.
He should have written out what is theta separately.
Sine inverse of
square root of cy.
Square root cy.
Okay, that's theta minus sine theta.
And then minus sine theta.
So sine theta is the square root of cy.
That is cy. And cosine.
So what is cosine? That's like cosine squared plus sine squared. Well, we know what sine squared. Sine squared theta is cy. So cosine squared is 1 minus sine squared. So it's 1 minus cy. No?
Theta is 1 minus sine squared, which is 1 minus cy.
Mm-hmm. That's cosine.
all square root. Yeah.
No, there's no square root. No. Right, because cosine squared. Right, correct.
Okay. So, and that's equal plus k, and that's equal to x, right? Because the integral of dx is just x. So this is our function x of y, parametrized, and it doesn't look too pretty. If I'm honest, you can't really see that it's a cycloid, which is supposed to be the solution from this. But when you plot it in Desmos or something, you get a fairly nice solution. This one is gonna...
How are you supposed to notice that this is anything?
hold only...
I guess if you've ever written the equation for a cycloid, you would notice that this is a cycloid. Who writes? I guess if you have a book of different geometric shapes, just geometry, just a book of geometric functions. Wow. Imagine just a book of geometric functions so that you would notice that this is a cycloid.
For y, a less than really nice solution. This one is gonna hold only for y, a less than 1 over c, right? Because of the square root. But y is always positive, which is good, right? So y is always positive in our problem. You never fall upward. So
what do you mean you never fall upward? Part of the cycloid is that it's going upwards. The way you drew it, part of it's going upwards. What do you mean falling upwards? So y is positive. What's with the 1 over c? Y is always less than y over c. Why would you say that? Where is that from? Because then it's 1. 1 minus 1 is a negative square root. So that's not allowed.
at least that's not a problem. Yep.
But what do you mean? Oh, you mean initially. So it can never go to y, to positive y, to negative y. So that's why it's greater than 0. That's what he meant by it never falls upwards. Okay.
Now we can try this other ansatz. The ansatz. Now I'm not...
What the heck is an ansatz? That's like guessing the solution? What is an ansatz? What is an ansatz? Based on the an ansatz is an educated guess or an additional assumption. A guesstimation, I guess. Oh my god! In German, Ansatz. Ansatzes? Ansatzi? Okay. Okay, it's just an educated guess.
Sure how they label x and y. I did look at this on, so at least that's not a problem. Yep. Now we can try this other ansatz. The ansatz. Now I'm not sure how they label x and y.
Why do you want to try something else? You have a solution.
I did look at this ansatz. So where are we? We want to look at this, right?
Wait, what's that? Didn't we take a look at that?
I believe that they say that y is phi minus sine phi and x is phi, 1 minus cosine phi. We would also need to have the identity of dx by d phi, because dx by dy is dx by d phi by dy. Okay, I think I'll leave that for another video then. I'll parameterize this and show you. But for now, this is the equation of the Brachistochrone. And without this I, obviously. That's it. And that's our curve of minimal time. I guess it would be nice to look at it, but you're going to have to type it into Desmos yourself.
What do you mean type it to decimals?
Thank you for watching. Bye-bye. Hello, friends. Welcome back to Quantum Quandary. Today, we'll be looking at the Brachistochrone problem.
Oh, I just replayed it instead of freezing it at the last frame. Okay, so this was the first time I've seen the using the Lagrange, the Euler-Lagrange equation. Now I'm beginning to get a little bit more of a grasp as to what it's trying to accomplish. Let me try. Let's basically start over with something maybe like this. Like, what is the Euler-Lagrange? More people talking about Euler-Lagrange. Nature takes this path.
Let us consider a particle in the gravitational field which is thrown vertically upwards from the height h1 equals 0 at the time t1 equals 0. It moves.
Yeah, this is the same problem as posed in the video in the previous. Oh, I didn't post the previous video. Okay, but this is, I guess, the standard way that Euler-Lagrange and Lagrangian mechanics is developed.
Moves upwards in the straight line and arrives at the ground at the same location h2 equals 0 at time t2. In the position time diagram, the particle has started at height h1 at time t1. Let us denote this starting point with A. And the particle has arrived at the end point B at height h2 at time t2. The connection between A and B must be a
Yeah, I'm not listening because I'm thinking about a meeting that I have in an hour and a half. I have to sit and meet someone. Let me see the news. Let's look at the news a little bit. This is very interesting. I really need to study this. Let's see if there's anything new today. Fractal woman. Steinmetz and the principle of incommensurability. Interesting. Boeing low-cost heavy lift vehicle. VTVL, SSTO, the big onion. So I was thinking, so NASA has a new engine, basically. They have an explosive, not just an explosive, not only a rotating explosion-based rocket engine, but also an air-breathing engine, which means soon we're going to be able to use jets to go into orbit. Simple jet engines will be able to carry us to orbit. That's the dream, but unfortunately, Greta is not going to allow this. As you can see here, this is basically Greta. The FAA delayed Starship Launch 5 for absurd issue. SpaceX. Okay, this is the fate of humanity. This is, nobody even knows for what. This is the FAA, not even for environmental reason. This is for safety reason, whatever that means.
Self-grounded. It sits idle, not due to technical glitches, but regular idle.
Oh, the audio is
Its
off.
ambitious goal of interplanetary travel. Starship. Hello, everyone. Welcome to the hyperspace. SpaceX's Starship program has captivated the world with its ambitious goal of interplanetary travel. The anticipation for each launch is palpable. We all eagerly await news of progress. However, the path to space is rarely smooth. Starship 5, the latest iteration of this mighty spacecraft.
They're talking about Starship 5 and they're showing, I think, the Indian, this is the Indian ship.
Finds itself grounded. It sits idle, not due to technical glitches, but regulatory hurdles. The delay has sparked frustration among space enthusiasts and SpaceX CEO Elon Musk alike. The dream of reaching Mars, of establishing humanity as a multiplanetary species, seems to hang precariously in the balance. The delay of Starship 5 is a stark reminder of the immense challenges that come with pushing the boundaries of exploration. The delay prompts us to ask critical questions. Is the regulatory framework hindering progress? Are we, in our quest for safety and responsibility?
Well, that is exactly the purpose of the regulatory concept. The regulatory concept has nothing but hindering process as its defined objective. That is exactly its only objective. That's literally it. Russian counterattack stalls. Ukraine hits back. Simulation of human body versus nuclear weapon. Cat eating Haitians. Yeah, I saw a video of what seems to be maybe a Haitian. I don't know, but he grabbed a cat and twisted its neck. So I don't know what that's about. I don't even know if that's an immigrant or that's an American. Who knows? And maybe he just got upset at the cat. So there's one video of one guy seems to be killing a cat. No, I don't even know for what reason. So terrible.
Inadvertently stifling the very spirit of exploration that drives us forward. These questions are complex and demand careful consideration. The answers will shape the future of space exploration. Elon Musk, known for his bold pronouncements and ambitious timelines, has been vocal in his frustration over the Starship 5 delays. He argues that the bureaucratic processes are unnecessarily slowing down innovation. He sees the red tape as a hindrance to human progress. Musk contends that the pace of rocket science should not be dictated by the slow grind of regulatory approval. He believes that innovation thrives in an environment of streamlined processes. In his view, every day of delay is a day lost in humanity's pursuit of the cosmos. His frustration is understandable.
Okay. Maybe spin equals angular momentum. Spin angular momentum after all. What is spin follow-up?
Angular momentum measures how much something is rotating. For a very brief time, a few physicists thought that spin was a type of angular momentum that came from the electrons spinning on their own axes. These days, we're pretty sure that that isn't the case. Electrons aren't actually spinning. But spin is still thought of as a type of
I don't know. I don't know if that's true.
angular momentum. It's referred to as intrinsic angular momentum. Angular momentum a particle just has without physically rotating. The idea always struck me.
That doesn't make any sense. How could that be? I mean, so rotation without actually rotating. So that sounds like a literal impossibility.
Is odd, and the two arguments I've heard for it seemed weak. The first is that in quantum mechanics, even though angular momentum and spin don't obey all the same equations, they do both obey one particular one. Then people claim that this equation defines angular momentum, hence spin is a type of angular momentum. I never understood why this random equation was so important. The other argument is what we looked at last time, the Stern-Gerlach experiment and similar. There, I thought the argument was that charged particles that have normal angular momentum act like magnets. Particles with spin also act like magnets, so let's just say that they have a type of angular momentum too, an intrinsic type. I thought that was unnecessary. Couldn't you just say that spin is an intrinsic magnetism instead? Isn't that a simpler explanation? In the last video, I asked you to...
Oh, that's good. Oh, so why don't you just say that it has an intrinsic magnetism? That would be simpler. Why do you have to say that it's spinning? Just some intrinsic magnetism.
To research spin for me, which you did a brilliant job of. I did the homework too by reading a bunch of things, and I realized that I was wrong about both these arguments. There is a very good reason that suggests that this equation. I did the homework too by reading a bunch of things, and I realized that I was wrong about.
Especially Sakurai's modern quantum mechanics.
Of both these arguments. There is a very good reason that suggests that this equation defines angular momentum. I'll explain why in the next.
What is this equation? IHL isn't random.
Couple of videos. But today I'll talk about why I was wrong about the Stern-Gerlach experiment. The angular momentum isn't just a useless byproduct, it's actually pretty crucial. And so maybe spin is angular momentum. The mysterious Stern-Gerlach apparatus is actually just a giant magnet. But a regular magnet wouldn't be enough, because if a little magnet was put into this field, it would be equally pulled up and down. Instead, the top bit is made pointy because that makes the south pole stronger, so the magnet is now pulled upward more. If the magnet was pointing downward, this south pole strongly repels the little magnet's south pole, so it goes downwards.
Wait 1 second, let me reduce the volume.
So you can start to see how this is equally pulled up and down. Instead, the top bit is.
Right, this is a uniform magnet. So if the Stern-Gerlach was using a uniform magnet, then it would be pulled up and down just the same.
Made pointy because that makes the south pole stronger, so the magnet is now pulled upward more. If the magnet was pointing downward, this.
Because it's pointy, then it's pulled up more. Why is that? Because it's pointy? So what if it's pointy? I don't understand.
The south pole strongly repels the little magnet's south pole, so it goes downwards. So you can start to see how this machine might measure orientation. It works fine for these two orientations, but here's the problem that bothered me for weeks. Imagine I put it in on its side. What we want the machine to do is not deflect the magnet either way. That seems fine. The magnet is equally attracted and repelled from both sides, but you can see these forces are going to twist the magnet. They keep twisting it until it's pointing in the upward direction. Now the force on the magnet is up. This happens to any magnet pointing at any angle. It gets twisted to point up. So by this logic, pretty much every magnet should go straight upward. The Stern-Gerlach machine isn't supposed to do this, so what's going on? It turns out I was wrong. This machine just doesn't work for little bar magnets exactly for this reason. But it does work when you have a charged particle moving in a circle. I was making a big mistake because I thought that these two things were essentially the same because their magnetic fields are the same. But the particles going in loops have one extra property that I completely neglected. They have angular momentum that comes from their rotation. We can represent angular momentum with an arrow. The length of the arrow represents how big the angular momentum is, so if we rotate the object faster, the arrow is bigger. The arrow also has direction, and this represents the direction the object is spinning. The arrow is always perpendicular to the plane the object is rotating in. The key thing about the angular momentum is it doesn't like to change. So that means it's hard to speed up or slow down the object, and it's hard to tilt it, because either of those things are going to change the arrow. Going back to our situation, if we have a rotating object and we put it in a magnetic field, just like the bar magnet, the magnetic field will try and twist it. But if it did get twisted, its angular momentum would change, and so unlike a bar magnet, it's going to resist that twisting, and that has a pretty unexpected consequence. Instead of twisting this way, its angular momentum traces out a circle. This is called Larmor precession. If you want to see the maths behind why this is, I'll explain that now. Otherwise, skip the explanation, and I'll just tell you why any of this matters for spin. For this explanation, we need our.
Isn't this just basically precession, like normal precession? If you try to modify. Okay, we'll see her explanation. Warning classical physics, this stuff is way harder for me than quantum. Skip to 642, we're 504.
Our classical mechanics. I'll do my best to explain this, but it took me ages to understand this properly, so don't panic if it's confusing. We need to introduce one more technical word, torque. A torque is something that twists an object. In our case here, it's from the magnetic field. Just like angular momentum though, torque is a vector, and its direction is perpendicular to the direction of twisting. The magnetic field is trying to twist the angular momentum.
Right. The way we denote it is that it's perpendicular to the plane of the twist. Out of the page, breaking the fifth wall. So tau is out of the page. What? Where is tau? I don't get it. Torque tau. Which is torque tau? She has so many. I see L. What is L? L means it's rotating over about L axis. Where is the axis for tau? And which is tau? There's so many arrows. What is going on? What is she saying here?
Need to introduce one more technical word, torque. A torque is something that twists an object. In our case here, it's from the magnetic field. Just like
it's from the magnetic field. But what's going on? What is L? L is not a what's going on? What is L?
Like angular momentum, though, torque is a vector. And
Okay, L is the angular momentum. So what did she say?
torque. A torque is something that twists an object. In our case here, it's from the magnetic field. Just like angular momentum, though, torque is a vector, and its direction is perpendicular to the direction of twisting. The magnetic field.
Okay, so let's assume, I guess what we're assuming is that there's two vectors. One is the angular momentum, that's L, so it's rotating about this axis with the right-hand rule. And then there's torque. It says out of the page. But the way you drew it doesn't make any sense. You didn't. Well, I don't know what she's drawing there. She's drawing an arrow. She's drawing some sort of an arrow. Where, if you want to draw something out of the page, you draw a circle with a dot. That means coming out of the page. Moving into the page is a circle with an X. That's the notation.
Field is trying to twist the angular momentum this way, so the torque is in this direction.
I don't know what she's talking about. Tau, easier to draw this way. Use your imagination. That what? Okay, so I guess the electron is spinning this way. Use your right hand rule to imagine how, right, this is your thumb. And the way your fingers curl creates the rotation about the orange arrow. Okay, so there's a rotation. And this rotation creates a magnet. That the north is this, I guess, and the south is this. Now, you also have a torque. And the torque is in this direction. I guess it's let's say the magnetic field is upwards, perfectly upwards. So you use the right hand second right hand rule with the 3 fingers. So the trigger finger is the motion of the moving particle, but it's not moving. But let's say the angular momentum. And then the thumb is the direction. The thumb is the direction of the magnetic field, which is upwards. So that's why it comes out of the page. It's not that the torque comes out of the page. Yes. The torque, the torque, I mean, the way she drew it doesn't make any sense. The torque, I mean, she didn't draw a torque, she drew a force. This is the magnetic force. If you imagine it now, then it's upwards. The torque is notated upwards. The way she drew it is incorrect, in my opinion.
Angular momentum is.
Let's see if anybody made a note. Oh, look, a science asylum from 8 years ago. Eugene. Is this the famous Eugene? Is this her responding? Looking glass. It's good that he gave us input. This is at 5:38. Has anyone noted something at around 5:38? This is from many years ago. I don't think YouTube used to support, here's 5:28. Are you using left-hand rule to get the sign of the torque? Conceptually, it doesn't matter, but would you mind clarifying? Yeah. I don't think she's using left or right. It should just be going up. Torque should be denoted as an up arrow at this time stamp. At this timestamp, torque should be denoted as an up arrow. So using the first right-hand rule, the torque would cause the electron to come out of the screen. Has anyone else noted at around 5:28? $5:30. Shouldn't your torque point into the page? No. From the right hand rule? No. I think your L vector should have been processing the opposite direction. No. This whole video 7 years ago. Well, I mean, we know what she wants. So I'm assuming that she wanted the electron to be forced to rotate out of the screen. In this case, the torque should have been an up vector. Then, using the first right hand rule, it should cause the electron to come out of the screen, I think. Did I put a comma? That's my opinion. Anyone else? She is my hero. She is my idol. Ti la 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 la. I don't see anybody else at around 5:30. Who did I just see that I recognize? I don't know. Awful. I think she died. And that's please articulate properly. Momentum. I get cancer every time you say momentum. Jesus Christ. Oh my God. I feel so dumb for not understanding anything. Oh my God. You're right. Classical mechanics are much harder than quantum mechanics. How can you say that? I honestly struggle with this a bit. This is from 9 years ago. Oh my God. So I have a chance, smart like you. I'm really not smart, but even for smart people, I think a lot of these problems are tricky. It's just doing lots of work on it that makes it easier, yeah. Oh. Completely off topic, but you might these pictures of nuclear physics lab I worked undergrad. Okay, this is from 9 years ago because today they wouldn't allow you to put a link unless YouTube doesn't recognize this as a link from Korea. Classical mechanics is non-intuitive. How can you say that? Khan Academies having educational video making content. Thanks, letting me know. I'll check it out. There's very few comments on this video because she wasn't famous. None of these big YouTubers were famous. They were all not famous. So whoever this is, Sandwich Ninja, I don't know who he is. I really like your argument about analogies, perhaps as you seem to suggest. That's all we can do in science, reduce the complexity of the world. No, no, no. Stop it. Stop it. Another link. Half a spin, example 3. Three years ago. I always imagine spin is spinning in another spatial dimension. Interesting. I had a think about that 9 years ago. Imagine we live in a 2D flat world. There's this 3D object. Anyway. Yes. Sakurai is the best. Also, a lot of material is advanced. Sakurai. Fn. Advanced quantum mechanics. Oh my god. If you're saying that this is the torque, this doesn't make any sense. Well, because then what you're saying is that this doesn't make any sense, that this is what the torque changes. You're saying that the torque processes, the torque goes around. That doesn't make any sense. You could say this is the force. We're forcing L, the angular momentum, we're forcing it to change, delta change along the tangent to the circle. So every time we're doing a delta change, every time we're changing L, just a little bit, just a little bit, just a little bit. Can that work? When I apply a torque on L, can we even do any vector addition? No, you're supposed to do cross vector, cross product. It's supposed to be a cross product, the way it's set up. So if it's an up, so if the torque goes up, I don't know. I haven't done mechanics in many years.
Currently in this direction, and we want to know which way it will be pointing in a very short time later, delta t. So we use this equation from classical mechanics. The new angular momentum equals the old one plus the torque times delta t.
You multiply torque by time? Torque is angular momentum change in angular momentum per time. Maybe that's torque. What's the definition of torque? What is the definition of torque? La 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 la. Oh, this is good. So this is torque. So the red is just the radius. The blue is the force. The green is the angular momentum. Angular momentum is just linear momentum times the radius. Torque is just the linear force times the radius. Okay, but how does torque change angular momentum? So torque is R cross F. So tau is R times the perpendicular projection of F, which is R F sine theta. Oh, there it is. So torque is a change, is the L dt. And L is I omega. So torque is I alpha, where alpha is omega dot. L is RP, L is R cross P, dl dt is R cross P, R cross dp dt plus dr dt cross P, but dr dt is 0 in our case. dp dt, yeah. So the LDT is R cross F plus the RDT is V cross P. But which V? Any change, okay. This is not just, this is any R. This is just the vector, just the location. This is the three-dimensional location. Where's R? Where's the definition of R? They never defined R. Wonderful. Where's the definition of R? Why don't you define R? Oh, maybe here? R is a position vector. That's good. A vector from the point about which the torque is being measured to the point where the force is applied. And R is the magnitude of the... Okay, that's good. So here it is. R is just a position vector. That's good. And you have F. This is the F in the perpendicular, F in the parallel. This is theta. This is good. And this is the torque. This is coming out of the page. So the force is this way. That's good. I mean, how could you say that this is more confusing than quantum? How could you ever say this is mechanics? It doesn't make any sense for anyone in the universe to say that this makes less sense than quantum. How can you say this? This is so straightforward. This is mechanics. There's like zero debate. No one has ever debated any of these points. You know what? Maybe in the old days they used to debate this like we debate quantum physics today. Who knows? Okay, so the LDT is R cross F because F is dp dt. That's correct. That's literally Newton's second law of motion. Plus the R dt is defined as V. That's good. Cross P. That's great. So the LDT is R cross F net. That's good. This is assuming, what are you assuming here? The cross product of momentum being with is associated with 0. Oh, V cross P is 0. The velocity cross P? The cross? Oh, the cross, of course. V and P are in the same direction. There's no cross. Cross is the projection, the perpendicular projection. There's no perpendicular projection. V and P, because velocity and momentum are parallel. That's good. Wow, that's genius. Amazing. So the LDT is R cross F. That's good. Okay, we don't need the derivative of the torque. I don't think so. The LDT is torque. This is torque. So torque is just R cross F. So if we go now, where is the video? Her video. So if we have a vector going up, this is the torque, and this is L. So just the force. What is the force? Just look at the force. This is the force. This is not the torque. This is not the torque. Is it? It's dl. This is dl. This is dl dt. This is dl. Is it? Is this dl? The torque is a vector pointing up. But the torque is dl dt. So how could this vector be the same as this vector? So it's not. This is the force. This is the force times the radius. This is the force applied here in this direction. This is not how we denote. This is not the torque. This is the force of the torque. This is the force at this arm. This is the force due to the torque. This is not the torque. Absolutely not. This has nothing to do with the torque. This is why she says she doesn't understand mechanics. Okay, 554. Okay, the purple, how do you spell purple? Purple, arrow denoted with tau is actually the force created by the torque. Torque equals R cross F. And so the purple arrow should be denoted by F. There should be an R from an R radius from the center of the circle to the orange arrow head. Orange arrow head. The torque should be an up pointing arrow from the, it doesn't matter where, from the base of the orange arrow denoted by tau. Okay, and that's all at 554. My God, she's so. And that, I mean, and that's how everyone gets so confused. So L plus D, this should be L plus DL. Tau dt, tau is dl dt. This is correct. This is correct. This is L plus dl. dl, well, tau is dl dt. dl dt times dt is dl. So this is L plus dl. So this happens to be correct.
Multiplying the torque by delta t just makes it smaller, and then we add
Multiply the torque by delta t, but this is not the torque. This is the force. Am I wrong? If this is the torque, then this means we're rotating something this way. This doesn't make any sense. We're trying to change L. This is dl. This is just dl. But if this is dl, then she's right, and this is torque. How could it be? This can't be. Well, it's a function of time. This doesn't make any sense. What does she mean by L? That it's rotating in some arbitrary direction, and there is a magnetic field going up. Otherwise, nothing here makes any sense. If the magnetic field is going up, but is the electron moving? If the electron is not moving, no, this is just magnetic field. If it's rotating this way, that means it has a magnetic field. This is the direction of the magnetic field, and there's another magnetic field. This is just two magnetic fields. I'm confused. I don't know what's going on. What this is angular momentum, and there is a torque. This is a force, but what's going on? I don't know. I'm confused. Maybe she's right. I don't know. This is L plus dl, so it makes sense. But this is not, this is dl. This is the change in the torque. This is dl dt. So if this is what we want to happen, so let's assume we want the electron to behave this way, to rotate, to precess this way. If this is what we want, how do we accomplish this? This is d, you could say this is delta tau. No, this is delta L. And delta L it's created by B. So you have, okay, but this has nothing to do with, let's ignore electromagnetism. So if we ignore electromagnetism, we just have a rotating object about the orange, and we want to change it to the red. So we need a vector like this, like so. That's fine. So how do we produce this delta L? So this delta L comes out of tau that points up. This is not tau. This is tau delta t. It's delta L. This is delta L. This is the change in the torque. This is not torque. What you're showing here is delta L caused by the torque. The torque should be denoted by an arrow pointing up.
Our old angular momentum. Using vector addition, the result is this vector. You can see how the angular momentum has started to turn around this circle. But if you think about it, the magnetic field is still trying to twist it, but now in that direction. So the new torque is this way. If we apply the rule again, the result is a vector even further along. And if we keep doing it, we can see that the angular momentum precesses. This was so hard for me to wrap my head around because this torque
Okay. But if you're just, you don't have to think about whatever she said. I don't see why she
in a very
needs
short time
to.
later, delta t. So we use this equation from classical mechanics. The new angular momentum equals the old one plus the torque times delta
Why don't you just say delta L? Why are you skipping steps?
t. Multiplying the torque by delta t just
Wait, let me see. I have a message. Mm-hmm.
makes it smaller, and then we add our old angular momentum. Using vector addition, the result is this vector. You can see how the angular momentum has started to turn around this circle. But if you think about it, the magnetic field is still trying to twist it, but now in that direction.
Why are you? I know it's hard to picture with my crappy drawings. It's not hard to picture. I just don't understand what you're talking about. That's not what's happening. It's always the same torque. Why would you say the torque is changing? This does what it's not that it's hard to wrap your head around it because it's hard. Rather, it's hard to wrap your head around it because it's wrong. I don't know what you're talking about. If that's what no, what are you talking about? At no point do you have such a force. What are you talking about? What? Oh my God. This is such a waste of time. And during this time, she was already doing her PhD or something. Oh my God. She doesn't have her fundamentals, at least at this point. I don't think she had her fundamentals properly, studied. This doesn't make any sense. You should just have an up arrow for torque, and it's always going to do the same thing. It's always going to cause L to change to precess, and that's it. Let me see if I can find, where are you getting this? This is 616. Has anyone spoken about this? This is so profound. You're so humble. Everyone is humble. I don't know. What is profound? What is profound? This is just wrong. It's just plain wrong. Ugh. This is just, you have angular momentum, you want to cause precession, so you just apply a torque up pointing arrow, and that should do it. Let me see if I can find a YouTube video. Okay. Okay. So this is classic physics, physique, posing. Classic physics or classical physics, torque, classical mechanics.
They're the most difficult concepts in all of 801.
No, all I want to see is, really? All I want to see is precession. Precession. Exactly.
Hi
Right.
there. If
Right.
you're
This is exactly right. This is gyroscopic precession. Is that it? Where's the torque? I don't know. Let me think. Where's the torque? So this is the angular. I can't even point at it. Let me take a screenshot. Okay. Well, didn't I just paste something? I can't paste it? I can't just paste something. Let me just make sure that you can't see what I'm trying to paste. Oh, you didn't see it at all. But I can't do paste. There's no right. There's no paste. You can't just paste something. So how can I show you something? There's no option to just paste. So I have to create a picture first and then I can paste it. Sorry, image upload failed. Oh, maybe I can paste it here? Yeah. Okay. So if this thing is rotating, let's say this way, right? He's using his right hand rule. So you have L along this. And now we're applying a force this way. So the force times a radius. Where's the radius? Well, this is the point about which all the rotation is taking place. So there's no force. This force is not interesting. So the only force that is interesting is through the center of mass going down. So it's this force times this arm, which means that's the torque. So the torque, okay. I'm beginning to understand that maybe she is correct and I am completely incorrect. Let me just write a note. Let me see. Let me just write a note, make sure. Okay. Let's see if he says, okay. Let me see, just make sure that we have a meeting in half an hour. Okay, anyway. Okay, so this is beginning to make sense. All right, so the force is down. Let's see the message. Wait, what's going on? I can't listen. Oh, he needs help with math? Oh my god. All right, let me just make sure. Yeah. Okay, so we'll do it tomorrow. That's good. Still, I have to grab a bite. I'm hungry. Anyway, so if so, all right, so the force pulls me down, and this is the arm, so it's R cross F, which means the torque keeps changing as, right, the torque at any given time, right? So this is R cross F. R cross F means the torque. Yeah, she's right. She's exactly correct, which makes perfect sense. So everything I said is incorrect. Everything I said is incorrect. I need to take everything back. No, wrong. Everything is wrong. Everything is wrong. La 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 la. So her delta L is basically delta tau. So delta tau and delta L. So let's delete. Well, we can edit it. Are you using left? No. She. Oops. So she seems to be correct. And I need to go grab a bite of something. Something, grab a bite. Something. Where's the other comment? Jesus help me. Oh my God, there it is. Okay. She is correct. Right? At 5:30, shouldn't your torque point into the page? No. No. Everything she did is correct. So she's good. Okay. We'll take a look at this. Let me just see messages. Harsh truth exposed by citizens after Trump versus Kamala debate. Oh, this is good. I need this. This is the energy levels. Open link. Molecular polarity. Wow, this is good stuff. Quantum navigation. Piers Morgan uncensored. Kamala did not win. Fiery debate on Trump versus Harris. That's interesting. Let's invite this guy to debate. Indefinite integral of inverse trig functions. This is always a good thing to go over. Theories, the universe as an open system. That's nonsense. Shows Miami social media model after car crash. Cops say she blamed pink cocaine. Interesting. Anyway, I don't think there's anything else that's interesting for now. So let's take a break and we'll come back and in bigger numbers. But I want to continue going over her video because this is good stuff. All right, see you later.